In this question, we've got water which is deflected by a fixed vane and produces two outflow jets. And the the diameters of the jets and the angles of the jets relative to the plane are given. And we're also given the inlet, the velocity of the inlet jet. So it's a bit more complicated to some of the other problems because we've got two outlets and one inlet, as opposed to just one inlet and one outlet. And we're asked to calculate the magnitude and direction of the force experienced by the vane, so the reaction force on the vane. So, always best to draw a sketch just to help visualize the problem. So, breaking it down, this is what's going on. So we've got one velocity going in, this is our inlet velocity. And we set up our coordinate system, so x being horizontal, y being in vertical. And then we have our first outlet jet, which has velocity c2 and is inclined 60 degrees to the horizontal, and our second outlet jet, which has velocity c3, has an inclined 30 degrees to the horizontal plane. So we can, since the outlet velocity is not stated, then we can assume that there's no friction and therefore that there's no losses. And therefore the velocity of the three jets are equal, so C1 is equal to C2, which is equal to C3. And if you're not sure about this proof, have a look back at the lecture, and I show that if we assume there's no friction, then this assumption can be made and is valid. And we now, because we've got a change in direction, we need to resolve and find the components of velocity in each direction. So if we consider our inlet, in the x direction we've got C1 velocity, and because this is horizontal, there is no y component of velocity, so that's equal to 0. And for the first outlet, which has velocity c2, the x component is cos of the angle, cos 60 times that velocity, and the y component is the sine of 60 times c2. So we're just taking trigonometry with that angle. For the second outlet, the x direction, we take the cos angle of 30, and for the y component it's sine of 30. But notice here that these signs are minus, and that's because relative to our coordinate system, in the y component it's going down, and in the x direction it's coming back towards us, so it's a negative component, whereas for the second outlet jet, it's C2, it's heading in both the positive x direction and the positive y direction. Okay, so this is the general momentum formulae. So this calculates the force on the fluid in the x direction. So it's the sum of the mass flow rate times the x component velocity for our outlet jets minus the mass flow rate times the x component velocity for all the inlets, and then the same but in the y direction as well. So applying this to our system, so in the x direction we have two outlets, C2 and C3, so we need to sum those together minus the sum of the inlets, and we only have one of those, mass flow rate times the velocity in the x, and the same for the y. Now, before we solve this, we need to first find the mass flow rate. And from continuity, we know what goes in must come out. So we have one inlet and two outlets. Therefore, the mass flow rate of 1 has got to equal to the mass flow rate of 2 plus the mass flow rate of jet 3. And substituting these for density times area times velocity, then we can write it like this. So for the inlet and the two outlet jets, we don't know what A1 is, we don't know what the area of the inlet jet is, and also we know that the densities are constant, and the velocities are constant, so those can cancel. So what we end up with is just that the area of 1 being equal to the area of 2 plus the area of 3. And we can work those out because we know the diameters of those two jets. We were given them in the question. So by using the area for the circle, we can work out the total area of jet 1 going in from the two diameters for jet 2 and 3. So now we have the area for jet 1, we can work out the mass flow rate for each of these jets. We know the velocities for each of them is the same, and we also know the density is the same, and it's for that of water. And so we can work out the mass flow rate for each jet. So we now have the area at 1, so we can plug that into this equation and work out that the mass flow rate is 147 kilograms per second. Using the area for jet 2 is 118 kilograms per second, and the mass flow rate for jet 3 is around 30 kilograms per second. So now we've got the mass flow rates. So we can plug this with the velocities for each component back into the formula that we got in the previous slide. So we had this formula for the force on the fluid in the x component. So remember, these are the sum of the outlet jets minus the sum of the inlet jets. So we put in the values we got, so the mass flow rate times by the velocity in the x direction plus mass flow rate jet 3 times the velocity in the x direction. But notice this is a minus, because remember this is coming back towards us in the x direction. So we need to make sure that we keep the right sign convention. Then minus the values for the first jet. And overall that gives us a value of minus 1,700 newtons in the x direction acting on the fluid. We do the same thing for the y component, so we plug in the values that we've previously found, and if we work them all out, that gives us a value of plus 1,310 newtons in the y direction. So just to summarise, the force that's acting on the fluid, and notice it is on the fluid, is a direction of force in the x direction of minus 1,700 newtons, force in the y direction of plus 1,310 newtons. But we were asked for the force on the vane, the reaction force, and because this is a force on the fluid that's on the vane is equal and opposite to that, so we just change the sign over. So now this is a force that's acting on the vane. Okay, so it makes sense, it's pushing it back and downwards, as you could kind of expect. So we have positive force in the x direction, negative force in the y direction. We can find the magnitude of the resultant force by using Pythagoras, and then we can finally find the angle from this force relative to the x-plane by taking the inverse tan of the two sides of this triangle. And if we do that, we end up with a final force of 2,150 newtons, which is acting around 38 degrees from the x direction.